Hello, good afternoon and good evening, everybody, and thanks to be here at our fifth webinar. My name is Stefano Gagliotto, and I'm the Chief of Sales here in ProGold, and today I will be the moderator. As always, I remind you that we have 8 webinars. This is the number 5, and they take place every week on Thursday at 4 p.m. chat time. The formula is always the same. There is a section of about 30-40 minutes for the presentation, and a second part about always 30 minutes reserved to the questions. You are free to do them anytime using the Q&A tool that you can find in the bar at the bottom of your screen. All the material we are going to talking about today, you can find in our website, progold.com. You can download the presentation and also the video. The title of today's work is Characterization of 18 karat gold alloys. This is very interesting because knowing the gold alloys characteristics will have or should help to get the precious information for selecting the most suitable composition for each jewel's production process. The speaker today is Elia Saccardo. He is graduating in material engineering. Here in ProGold, he is responsible for the R&D of our direct precious metal 3D printing business unit. I remind you that we are going to have in the last webinar, the number 8, we will talk again about 3D printing. So it's interesting, and we hope you to see you at that webinar. I think that I've said all, and we can start. I can pass the word to Elia, wishing everybody a good listening. So Elia, it's your time, and good luck and break the leg. You can go.
Okay, thank you, Stefano, for your introduction, and welcome everybody to this ProGold webinar. We are going to talk about characterization of 18 karat gold alloys. So in this research work, we studied 18 and 14 karat gold alloys, both colored and white alloys. Today, we will present the results obtained for the colored 18 karat gold alloys. So usually the first requirement for an alloy starts from the color of the alloy. So color, we can say that is the most important feature of a gold alloy, since most of the time customers start from a color request, and then starting from the color, and depending on which production process it goes for, we need to select the minor elements that could be the oxidants, the oxidizer, or grain refiners. Basically, we will talk about quaternary alloys, so alloy made of gold, silver, zinc, and copper. And for this work, we use our commercial alloys, but we hide their names to treat them in a scientifically manner. So thus, we divided all the considered alloys in 2 big families: the alloys for investment casting, so casting alloys, and wrought alloys, so alloys for plastic deformation. We now going to present the experimental step, the experimental procedure that we built in order to test the alloy in a scientific way and to get a characterization method that is basing, when possible, on existing standard. So mainly the standard comes from steel world, but we apply them in the gold manufacturing. And following this standard during this research helped us to get reliable and repeatable results. So the first test we perform is the DTA analysis. We determine the SOLIDUS temperature and the LIQUIDUS temperature that are very important in order to cast the alloy, both for casting alloys and wrought alloys. So through the same machine, we also performed the DSC analysis that gave other interesting parameters, such as one used, for example, in the casting simulation software, but we didn't consider them in this work. So just you to know that we have this data for our alloys, and if you need it, you can ask ProGold. So the second test we did is the density measurement. To do this, we rolled an ingot to avoid porosity defects and so on, and to get a reliable value of density. And then we follow the Archimedes method that is based on the formula you are seeing in this slide. So we got all the density for all the selected alloys. Another test that we perform is the Ericsson test, or deep drawing test. That is a standard test. It follows an ASTM standard. The principle is that a spherical punch is pressed against a 0.4 millimeter thickness sheet, and it deforms it. We measure the depth of the indentation before the breakage of this lamina. And this is very important for wrought alloys, so for plastic deformation alloys, and to understand if an alloy is suitable for the production of stampato and double stampato that is made by deep drawing technique. We then perform the tensile test, and as per the ASTM standard, we do this test for both the family of the alloys, so casting alloys and wrought alloys, and we obtain the UTS, so the ultimate tensile strength of the material of the alloy. That is the maximum strength that the material can support before breakage. Then we measure the yield stress, that is the stress under which we can avoid to deform permanently the material, and then finally the elongation to breakage. For casting alloys, we cast a flask with the specimen already ready for the tensile test. Instead, for wrought alloys, we cast a square ingot and then we roll it in order to get a wire, and we perform the tensile test on that wire. Another test is the hardness test, very important. Also, this one is following the STM standard guidelines. We determine the hardness of the alloy in different conditions. So after cold working at 40, 60, 80, and 90 degrees of rolling reduction of the formation, and after annealing, but also after solubilization annealing and precipitation hardening in 9 different conditions that we will see later in the presentation. Then we measure for all the alloys the grain size. So grain size of the material is obtained by polishing the sample and then etching it with cyanide solution to make visible the crystalline structure. Then we count the grain by using the Jeffrey method, that is a standard method. These tests help us to determine, as we say, the grain size. So the grain size is very important because it influences many properties of the alloy. In particular, it affects the mechanical properties, as we know. So big grains mean less resistant, because you can imagine that it's like a crowded room full of people. If there is less people, the mechanical resistance, we can say, is less than if there is a lot of people taking by hand one to each other and very close one to each other. So the grain size is very important. Then we measure the color. As we say, the color of the alloy on the precious alloy has an important role in the alloy selection. So it doesn't depend on the process on which an alloy is going for, but it's important for the quality and the aesthetical reason of the final object. To determine the color, we use a colorimeter in order to get reliable and objective results. And I mean that the color of gold alloy is not so easy to be distinguished one to each other. And also, the human eye is looking at the color of the alloy differently from person to another person. So it's important to have a method that could give us some values that in our case are 3 coordinates called L, A, and B that compose the three-dimensional space of color. We will see it later. So to make the specimen we use for this research, we start from pre-melting, and then we do the DTA in order to determine the temperature at which the alloy has to be casted. And we differentiate the kind of casting we made. So we have 3 kind of ingot casted and 2 kind of flask. So each one of those bring 2 different samples for different tests. In the next slide, we will present the technical parameters and details that can be useful for who of you wants to repeat the procedure, and so I will pass them in a fast way. So the first ingot is done for the hardening curve, and we collect the hardness and all the measurement for, as we said, 40, 60, 80, and 90% of cold deformation for the broad alloys. Then from these same ingots, we also obtain the density measurement and the color test and the annealing test. Another ingot helps us to obtain the metal sheet used for the deep drawing test. So we roll the ingot to 0.4 millimeters. The last ingot was used to, it was a square ingot, and it was used for the production of the wire and the following tensile test, as we say. Then the first casting was done with some metal, some very simple square sample, in order to get the hardness after casting, after heat treatment. Here we can see the 9 condition of the age hardening, as we mentioned before. So we have 250 degrees C, then 300, then 350 for 1 hour, 2 and 3 hours. The last flask was used to obtain the tensile test for casting alloys. So already they have the shape that we want to use to test the tensile properties of the material. Even if we follow the testing procedure given, for the STM standard, the dimension of the specimen is smaller, and this was just to avoid use a lot of precious metal, but we maintain all the other parameters. So finally, we have here the temperatures, timing, and cooling condition for the annealing heat treatment and solubilization annealing heat treatment, so solution annealing. Okay. Into this slide and in the following one, we will present the composition of the 34 alloys used in this research work. They are sorted by increasing content of silver. And as we can see, there are also some minor elements. So is the GR1 and GR2, that means grain refiner 1 and grain refiner 2, and also the oxidizers. So let's see the second part of the table. The content of silver range from about 2% of silver to 19%. Okay, the description of the experimental and technical part is concluded, so we are coming to the outcome of this project. So basically the results we obtain. Let's start from the LIQUIDUS and SOLIDUS temperature, very important. They are represented from the interpolation curves you can see. So the up curve is the LIQUIDUS temperature, and the lower curve is the SOLIDUS temperature against the silver concentration expressed in part per thousands, in thousands. So to build the trend curves, we didn't take in account the alloys with more than about 12% of zinc, because those alloys are quite difficult to be casted, or better, high content of zinc can give some problem during casting, for example, but we can see those alloys in the bottom part of this graph, and we can just understand from here that the addition of zinc, so a high amount of zinc, will lower the SOLIDUS and LIQUIDUS temperatures. Regarding silver, as the content increases, both LIQUIDUS and SOLIDUS temperature initially decreases, and then they increase again. Okay, another interesting aspect is the melting range. As you can see, the silver, as the silver content raises, the melting range increases. So it means that the difference between the LIQUIDUS and SOLIDUS curve are becoming bigger as the silver concentration is becoming bigger. This could lead, for example, a different behavior of the alloy during solidification, for example. As we know, big melting range could lead to some problem as shrinkage porosity during solidification, but it has to be studied for each single composition, because it's not directly linked to the shrinkage of the alloy during solidification. Okay, let's talk about the density. So we can see that as the silver concentration increases, so the density will increase. And in this case, it was an expected result. This could make the difference, for example, if a customer sell the alloys by selling it at pieces or by selling it through a weight mode. It's not obviously that if you sell at weight, you have to decrease your silver concentration and to put, for example, zinc, as we know that also zinc influences the density value. But you have to take in account that changing the composition to decrease the density could lead to other problems during casting and during the production process. Talking about color, we said it's very important as alloy characteristic. So the colorimeter gives 3 values that are L, A, and B. These 3 values are the coordinate of a 3-dimensional color space. L is the first one, and it represents the brightness of the alloy. High value of L means that the alloy is very bright and shining. Rising the silver content, this L coordinate is increasing. So it means that the alloy will be brighter, will be more shining. And this is probably due to the fact that silver has an high reflectivity, and so it increased the overall L coordinate of the alloy. During the investigation, we understand that also zinc has almost the same effect of silver on the L coordinate. Let's see now the second coordinate, color coordinate, that is the A, and it represents the color component going from red to green. Obviously, we passed through the yellow gold, and so green, it means not properly a green alloy as we intended as green color, but there will be pale yellow with green reflection or green background tone. It's pretty difficult to explain the color without seeing it, but we can understand that the increasing concentration of silver is moving the A coordinate from red to green value. So even if the color metals are only gold and copper, and the other elements are mostly grays, we can say, the combination between silver and the rest of the alloy gives this greenish aspect, especially, as we said, for high content of silver in the alloy. Then we evaluated the zinc content, as zinc affect the A coordinate. So in this case, we discover a very important thing, so that zinc is moving the A coordinate in a double way, so with double power, we can say, than silver. And that's why in this graph, we plot the A coordinate by changing the sum of silver plus 2 times the zinc. And this is why, as we say, the zinc has a double whitening power than the silver one. It has to be taken in account that zinc gives a color that is not identically to the whitening effect of silver. The alloy with high content of zinc will be less shining, so with more pale yellow effect. It gives to the alloy a sort of grayish tone. That's why we cannot substitute the whole quantity of silver with zinc without consequences. A part of the consequences deriving from the production process, we have to take into account also that the final color won't be the same. So in some countries, for example, they prefer using more cheaper alloys, and so they bought low silver and high zinc content alloys. But they know that the final quality, they can accept lower final quality. It's not the same of having high silver content. Okay, let's move to the B coordinate. This coordinate is instead increased by an increase of silver content. The B coordinate represents the color component going from blue to yellow. And this means that the alloy will become more intense yellow by adding silver. We could imagine it since silver makes the alloy brighter. So even in this case, we can say that the alloy will become more yellow in a certain way, more deep yellow. Evaluating the effect of zinc for B coordinate, we discovered that it has almost the same effect of silver in changing the B coordinate. That's why this time we represent the coordinate B in function of silver and then of copper, that is the difference of silver and zinc content. So here it is the copper concentration that influences the B coordinates. As you can see, we are shifting from blue to yellow, so it's the opposite of silver, obviously. Okay, let's talk about now the hardness of these alloys. So all the alloys have been considered, and we performed the hardness test on the solubilized alloy and on the maximum hardness obtained after the H hardening. So the triangles here will present the maximum hardening value, maximum hardness value, sorry, for all the alloys, while the lower point of these curves are representing the solution heat-treated samples. So silver content decreases the hardness in both cases, and the more it is, and the less hardenable will be the alloy. And zinc has only a little effect on the hardness of the alloy, but more investigation will be necessary to understand this. So now, by looking at the hardness value we obtain, we understand that the silver and zinc are not the most important elements for the hardness of the alloy, but the most important one is the copper concentration. So that's why we plot both the hardness before the hardening and after hardening on the copper concentration. Copper is affecting more than the other elements because it creates an ordinate crystalline structure with gold that is very hard. And so the higher the content of copper we have in the alloy, the higher will be the hardness. Also, the alloy with high content of copper are more hardenable. As we can see, the difference between the two curves is increasing with the copper concentration. If we look here, for example, pale yellow, light yellow gold, for example, 2N standard color or 3N color, are only partially hardenable. And in order to get enough hardenable effect given from the copper concentration, we need to put in the alloy at least 8 or 9% of copper concentration. So the hardness increasing for 2N color is not so important. So it's important to evaluate if an age hardening heat treatment will be will worth the little increase in hardness. Could help to increase the hardness, for example, for polishing, for finishing the items, because the higher the hardness, so the easier will be to polish the sample. From the 3N yellow color, we can say that the alloy is well hardenable, so you will raise more than 30, 40, 50 Vickers after age hardening. Okay, testing the effect of composition on the average grain size, we can see that the grain refiners and the oxidizers have important role on it. In particular, the oxidizers increase the grain size, and this is also a reason why it's not convenient to use deoxidized alloys for plastic deformation, because the oxidizer tends to increase the size of the grain. So it lowers the mechanical properties of the alloy. As we can see regarding the two grain refiners, so the two trends that we can see here, the upper one is referring to grain refiner 1 and the other for grain refiner 2. The grain refiner 2 is working very well to maintain the grain size small at any concentration of silver. Grain refiner 1 instead is that is cobalt, so we can say grain refiner 1 is cobalt. It's not working very well because as known, cobalt is well working as grain refiner at solid state. Here we collect the data from the liquid state, or better, we are looking at the grain size after solidification of the alloy. And cobalt is not efficient in this. Increasing the silver concentration, it helps because the grain size is decreasing also for grain refiner 1, but it's not so efficient as grain refiner number 2. So ProGold removed the alloy containing grain refiner 1. Firstly, because of its low efficiency while the solidification of the alloy, but also because it is a possible candidate for toxic elements list. So we avoid to use these possible harmful elements, and we designed some new alloys specific with other kind of grain refiner that is coming from the platinum group usually, and they are most effective on the grain size for both casting and annealing, so in liquid state and solid state. Okay, we are going now to see the test performed on the alloys specific for the investment casting process. So we take the alloys, as we said, we avoid taking the alloys with grain refiner 1, as we just said. Grain refiner 1 is not working on the liquid to solid process. And then we take only alloys with grain refiner number 2 and deoxidizer. So let's see the results. Here we are talking about the UTS, so ultimate tensile strength, and the yield strength. So we can see that the trend plotted for these alloys with grain refiner. So both the mechanical properties, the UTS and the yield strength, are decreasing with an increasing content of silver. So regarding the alloys containing the deoxidizer, it is clear that they have very low mechanical properties in comparison with the grain refined ones. There is no evident trend for such alloys, and this graph could add, for example, if you are producing casted items, it's not always required to use deoxidizer. If, for example, you have to cast very light object or thin details objects as, I don't know, net structure, you better to avoid the presence of deoxidizers, because the alloy containing deoxidizer could not have enough strength to be handled. And so sometimes it's preferable to have less protection during casting of the alloy that is given from the deoxidizers, as we know, but it's better to be sure about the mechanical properties. So sometimes it's not directly given as good to take an alloy with a deoxidizer instead of one containing a grain refiner. There is no real trend for the deoxidized alloy. Looking at the elongation to breakage, there is not an evident trend also here. It seems that for the alloys with grain refiner number 2, so the triangles, there is a little trend that increased the capacity of the alloy to elongate before breakage with an increasing silver concentration. So the zinc instead seems to give an opposite effect. High zinc content have less elongation. And as we saw before, we can clearly see that the presence of deoxidizer lowered the mechanical properties. In this case, is lowering the elongation to rupture. Let's see now the alloys for plastic deformation. So as we see, we don't have anymore the deoxidizer elements, but we have only grain refiner 1 and grain refiner 2. Looking at the same properties as we say for the casting alloys, the UTS and yield strand has here an evident trend, and the silver concentration lowered the properties, both for grain refiner 1 and for grain refiner 2. So the trend observed for the grain size is confirmed in the sense of we saw before that grain size is increased for higher silver concentration, and this is according to this trend of the UTS and yield strand. For this case, grain refiner number 2 seems to be more efficient than grain refiner number 1. The difference must be noticed that the difference between the 2 grain refinery is lowering while increasing the silver concentration. Here the drawability. Okay, the drawability is very important for a particular item's production. So for example, if you want to do stampato, as we say at the beginning, is important these properties. The drawability or deep drawing capacity of the alloy will change just a bit on the silver concentration. There is a sort of trend that we can say, but not so clearly. And the bigger the content of silver, and the higher will be the drawability of the alloy. But the most important things for drawability is the zinc content, since we discovered that zinc and grain size are the most influencing properties on the drawability. So the much more zinc I will put in the alloy, and the higher will be the grain size. So more easy you can draw your alloy, you can perform deep drawing on your metal. Finally, we are going to see the work hardening curves, and so how the hardness will increase through the cold working of the alloy. In this case, we start from low silver content alloys that are represented from the top curve, and high silver content alloys, that is the bottom one. We expected these results before the test because the fact that all the curves are parallel, it means that the hardening of the alloy is not depending on the thickness reduction, so the percentage of cold working, but it is only influenced on the starting hardness of the alloy. As we can see at the beginning, a higher silver content is giving lower hardness, and so the final hardness of an alloy with high silver content will be lower at high cold deformation than low silver content, just because the content of copper is different. As we said, copper is very important for hardness. Okay, so we saw a lot of tests. Is a huge quantity of tests performed from ProGold, and all these tests also for 14 carats, yellow, red gold, white gold, also for white gold 18 karat that we didn't present it today. So this huge amount of data helps us to understand how the composition of the alloy will move all the properties, will influence the properties, the workability, and we can understand from all this data if an alloy is suitable for a certain production process, or if it's better to change just a bit the composition accordingly to the customer request. So in this case, some data was missing. That was the data missing on our commercial alloy. So we performed other kind of tests, doing some specific composition created to fill the gaps in this research. Also, I want to say that for each request you have, so if you have doubt in which alloy to select before starting the production of new items or new products, just call ProGold, and all the technician of ProGold will help you in selecting the correct alloy with the correct composition, and for sure suitable for your need and your production process. So at this point, I would just say thanks you for the attention, and I will give the word back to Stefano. Thank you.
Thank you very much, Elia. Very good presentation. As Elia said, we remind you that in case you want to go deeper discussing about any topic, you are free to write us, sending an email or any kind of request using the email addresses that you can see in this last slide. There is mine as well, and also the Elia one. So I also remind you that we can go ahead right now, okay, discussing and trying to answer to all your questions. Okay, so Elia, I think that we can start with the first one. Okay, from Mr. Nuriono. Okay, sorry for the pronounce. What is good characteristic alloy for lost wax casting? by hand, make by hand, which this is quite general, where there is like with less porosity or less inclusion. There is also a second part of the question, and I will answer personally. Okay, so you understand it, yeah?
Yes, yes, I got the
okay.
question. So in this case is a quite general question. So to answer this, I would just say that the presence of deoxidizers in alloys for investment casting is very, very important, because even if you use all the correct procedure, I mean, to protect the alloy from the oxidation by using inert gas, and even if you have a closed system to cast or open system, it doesn't matter. The presence of the deoxidizers such as silicon or germanium or similar elements will help a lot in reducing the porosity. Also because during casting and investment, the high risk is to get some reaction between the investment and the alloy. In the previous webinar, I think that Daniele Maggian explained about the role of zinc and silicon for investment casting. You can see also that webinar on YouTube, or you can write us, and there was a very detailed explanation on how to prevent defects in casting, especially for gas porosity, for example, that is coming from the reaction between the alloy and the investment. To avoid inclusion particles dirty in the alloy, our suggestion is to work in a clean manner and in a proper manner. I mean, do not use more than 40 or 30% of scraps inside the alloy, clean very well the scraps, and so on. There is a list of well-known practice advices that could help you to increase the quality, to decrease the scraps coming from the castings.
Okay, I would like to try to answer to the second part of the question, which is, what is ProGold alloy 18K suitable for the above question that Elia answered right now?
Yep.
It's quite difficult. I mean, the problem are general. Usually, I think it's wrong to say that we have a best alloy. Okay, so the right answer is understanding, suggesting a kind of alloy, understanding what is the problem you are really facing. So also porosity, I understand porosity, but porosity, we can have different kind of porosity and different kind of inclusion. So that's why in our range there are a lot. For sure, we have the right one for your problem. So if you want, okay, as we told you, we are available to discuss personally. You can share, for example, picture or about your items where you have problem. We will be happy to try to suggest you how to solve and which is the right alloy to use. We go with the question number 2 from Mr. Arul Kumar. What is the correlation between the filling rate respect to the melting range?
Sorry, can you repeat?
Yes. Is there a correlation between the filling foam filling rate respect to the melting range?
Okay, yes. I will take the slide of melting range. Just give me a second. Okay. So as we said, an increase in silver concentration, but other elements will modify and in different ways, increasing or decreasing the melting range. So in this case, silver is increasing the melting range. Increasing melting range, it means that the alloy will stay liquid, or better, partially liquid for longer time after casting. So the solidification, in a certain way, we can say it will be longer. Longer solidification will have bad effect on the creation of shrinkage porosity, for example. So also for filling effect is partially related to the melting range, because the form filling capacity of an alloy is depending also on other kind of parameters, such as viscosity, liquid viscosity of the alloy, or for example, on the simple casting temperature. If you have for filling problem, for example, you can try increasing the flask temperature or the metal temperature before casting in order to maintain the alloy more fluid, so to decrease the viscosity through the temperature. I don't know if I answered to the question.
Okay, thank you, Elia. Mr. Arukuma is still asking also, are you doing any test to check, I mean, the foam filling rate measurement? If yes, can you explain how you are going to measure, okay, how it's working, the foam filling?
Okay, this is a quite complicated answer to give right now, but yes, we studied it. We have another very interesting machine here in ProGold in our R&D lab, that is the dilatometer. And this dilatometer measures the expansion or shrinkage of the alloy during the temperature changing. What is very new for us, new in the sense that is not common to have this instrument, is that our dilatometer is measuring also the shrinkage happening to the alloy while the solidification. So when we start from the liquid phase and we go to the solid phase, we can measure how much the alloy is shrinking. So is everything presented in another work, and the answer is quite difficult. So I think it's better, I suggest to this person to write us, to send an email or call in ProGold, and we can discuss it deeply, directly with him.
Okay. He's also asking to check the microstructure. We are using cyanide. Okay. Is there any alternative elements that we can use for the same purpose?
For gold alloys, it's quite difficult to avoid cyanide. There are some other solutions based on chlorine, I think, and something like that, but they are not giving results as the one we saw at the beginning. So this kind of evident microstructure is given only from cyanide. The solution is very low in concentration of cyanide. I mean that the cyanide concentration could be around the, if I'm not wrong, 0 point something or maximum 1–2% in the solution. But it's dangerous, this kind of solution used, so be careful in using it, and you will get these very beautiful results. Also, the grain size is looking so good, as so to say, because of a carefully polishing of the sample before. Because if you use cyanide, for example, in sample coming from the casting without a perfect mirror polishing, you cannot obtain the crystalline structure visible.
Okay, and always Mr. Arulkumar is asking how much is the volume shrinkage? Okay, I think how much is changing the shrinkage if you check between yellow gold and pink gold. I think that the meaning is understanding which difference are there in terms of shrinkage between yellow and red gold, 18K.
Okay, same as before, there is a publication in ProGold website that you can read by yourself, and if you want us to explain that these features of our alloys, we can talk it apart of here. I think it going out of the topics of this webinar. But we are available to answer this question, and we have also interesting results about it.
Okay, and always talking about foam filling, which looks to be a complicated problem, but yes. I well understand is if foam filling property of yellow gold is usually higher than pink gold, is there a way to overcome and play with some composition changes? Just to, I think the meaning is getting the proper properties of in pink gold that we are able to get in yellow gold.
Yep. For sure, there are some elements that decrease the viscosity of the alloy, but as we say along this presentation, it's always a kind of compromise between properties, because some elements will help the alloy to help for filling, so you will have less empty part of your, I don't know, complicated items, for example, but you have to take in account that the most complicated, so the as many elements you put inside your alloy to increase a property that you're looking for, you have to accept that other characteristic of the alloy will be less performant. For example, in the case of zinc, we know that zinc for casting is not good, but as we said, for drawability is excellent. And if you are available to accept some compromises on the alloy, there are some elements that could help the form filling and the viscosity of the alloy. But first of all, I will answer that the most important parameters for filling is the temperature.
Okay, Mr. Osvaldi is asking which is the best alloy to work in casting and work, I think, plastic deformation, and what methods can I use it? Can I use for it, for example, oxygen and gas?
Okay, I think this is a kind of a commercial question.
Yeah.
So,
you can say something after I can go.
Yes, so the so-called universal alloys that you can use both for investment casting and plastic deformation are the alloy containing the grain refiner. As we say, okay, let me find the correct one. This one, sorry. Okay. As we can see here, the mechanical properties of a deoxidized alloy are not enough to use that specific alloy also for plastic deformation. So our suggestion is to take care of a grain refined alloy during investment casting, because it's easier to use an alloy for plastic deformation in general, also for casting, than the opposite. So in this case, we will suggest a grain refined alloy. Independent of which color, we can suggest the specific code of ProGold alloy.
Yes, let me tell you something more. So the point is that we have universal family of alloys that can be used for all kind of process, but also we have something which is perfectly suitable for any specific request. So as Elia was saying, many times is a compromise issue or matter. So it depends also in what you really want to do. And also talking about this, if you want, we can talk in a private way, okay, directly by email, by phone, and according in what is your really need, we can find out the right solution for you. The same person is also asking if we are selling in Colombia. Yes, of course, but not directly through a dealer. Okay, we sell directly. And also for this reason, we'll be happy to stay in touch with you later. There is another question from Mr. Vagesan. Okay, as you have tried out with a lot of alloy composition, from that, what was the specific perfect alloy composition for high hardness without generically mentioning that have more concentration of copper and low concentration of silver? I think he's talking about 18K. Yeah, of course. Sorry, or 18K. Yes. You understand, Elia?
Which color of the alloy?
It's not mentioned. I think I will try a lot of composition for what was the specific perfect alloy composition for high hardness. Without generally mentioning they have concentration of, so I don't know. So let's try to tell something about what is the meaning in terms of hardness in 18K if you put more copper or less copper, balancing with the silver, so red and yellow. Hoping that we are able to answer them in this way, because it's not well clear, the question.
Only talking about 18 karat alloy, The most important, as we said, is the copper content, because it's the only one that has a hardening effect on the alloy.
Sorry, Elia, sorry, I'm
Yes?
sorry. Yes, he's talking about yellow gold. Okay,
Okay,
so let's
yellow
say
gold.
3N, 2N, something like that.
Yes, exactly. As we say, 2N color is the lower limit of the hardenable alloy. If you use color brighter, so yellow color brighter or whiter than the 2N standard color, it's very difficult to get an hardenable alloy in 18 karat. If you're talking instead of 14 karat, is everything changed, because in 14 karat is not the copper that is driving the hardness, the main hardness of the alloy, but there will be other elements influencing the hardness. So next week, in the webinar of next week, we will talk about specifically of 14 karat alloy. So we suggest you to follow also the next webinar. Talking about 18 karat, there is no other way to make the alloy harder instead of copper concentration. Obviously, other if you, for example, if you use a wrought alloy, you can deform it to increase the hardness, but it's not every time a useful solution, because sometimes you just have to cast and then to do an edge hardening. So in this case, the copper and the grain refiner will help you. I just want to say that also the grain size, small grain size, could help in the mechanical properties, hardness also.
Okay, Mr. Murtuza is asking, do same type of mechanical characteristic of alloy required for wire drawing and pipe drawing process?
Okay, wire drawing and pipe drawing are very, very similar process. They change just because of the shape, but the drawing is a general characteristics of the alloy. So in this case, they won't change a lot, but the stress on the material will change. So there is not a composition better than the other one in the case of wire and in the case of tube, but there are some advices on how to deform the material. For example, on the pipe drawing, it's important to maintain a specific ratio between the internal diameter, external diameter, so to decrease the thickness of the tube in a certain way, because if you go since drawing is a very stressful process on the material, it's important to avoid going over the maximum cold working that the material can support before the annealing. And there is a lot of little advice and little trick that you can perform in order to get the best result possible.
Okay, Mr. Murtuza is also asking if the mechanical characteristics and overall grain structure remains the same after solution annealing in two different cases. 80% reduction, 55% reduction. I mean, it's very, very specific question. So I think that he's asking if and how the grain structure is changing after reduction 80% and 55%, okay, which is some specific kind of reduction. Okay. And how they change with the annealing.
Okay, to be explained, this answer will need some very specific scientifically training that I won't annoy you with these details, but in general, during the annealing, the grains of the materials that has been deformed previously, they are elongated because of the formation. So you have a very small and break grains, we can say, because the grain is becoming elongated, smaller, and also not regular as in the as cast state. To answer your question, we can say that the grain size will be bigger for the case of the lower cold deformation. For example, you say 60 or 65, I don't remember. Anyway, if you deform the material more during the annealing process, the grain size will remain smaller because you deform it more. So in a certain way, you take a lot of energy and you put it inside the material. And this energy is helpful during the annealing process because it helps to regenerate the grain, so to create new little grains. So the more you deform, and the more you will get some small grains after annealing, obviously at the same annealing condition.
Okay. Mr. Nishan is asking if we have any solder, I think, master alloy for pin gold. Also here, if you want to say something, Elia, it's very, otherwise I can go.
Okay, you can answer this question, I think.
So this is a general question. If I well understood, okay, that you mean about solder. It is not easy. It's not easy. It's quite impossible. This is a natural defect because, as you know, to get the right temperature to have the soldering phase, you need to drop the melting point. So you know that to get in the red gold or pink gold, we need to put a lot of copper, and so to reduce the melting point, we need necessary to add other material which are gonna changing the color, the red gold. So as lower you want the melting point being able to make soldering, higher will be the loss in terms of color. So this is how to say a kind of, it's not a point that we don't have. It's a like kind of natural limit. So we have, yes, the answer is we have, but don't think that if we talk about 5N color, we have the solder with the same color. So necessary has to be a little bit, we can say that it's how to say yellow red alloy. Okay, so it's not red, but of course it's not also yellow, but it's necessary. You cannot, otherwise, if you want to have the same color you can get in 18K for the red gold, you cannot have the temperature, because it means that you have 90% copper in the alloy. To have the same color, you should put 90% of copper also in the soldering, which means no soldering phase. So we have, but it's not the color that some usually people expect to have. There is another question, I think also this is quite commercial, from Mr. Madhavan. Is there any alloy for 18K yellow gold matching and having the same color we can get in 22 karat gold? Also here, we are talking, so the answer is, in a mathematic way, no, impossible. But we can go close in somehow, because the point is also always that the color is coming out from the quantity of gold present. So we are talking of 18K, there is 75% of gold. In 22K, gold quantity is much bigger. And so the yellow effect of the gold is having an effect. So also if you play with different composition of the alloy, it is, how to say, quite impossible getting exactly the same effect. This is also another natural defect, natural problem due to the fact that the quantity of gold we are talking about are different. But for sure we can reach. And that's also about the LAB coordinates that Elia was talking about before. We have many chance to make many tests, reaching and helping you to go as close as possible to your requirement to have the same effect you're getting in 22 karat. There is another question, which looks to be the last one. What is the temperature? Okay, so this is very general. Is what is the temperature for continuous casting machine when you go with pin gold? Yes, so this is the question, let's say.
Okay. I think it's better you to write as, because it depends a lot on the alloy, on the color of the alloy. And so if you write as an email or you call, whatever you want, we can talk about this deeply. I think it's not we cannot answer temperature in general, because there is not. It's specific for the process and for the kind of the alloy you are trying to cast.
Okay, he looks that there are no more questions. So I will give you the reminder for next week. If in the meantime you want to add something, please go ahead. Elia is here for us. So
Yes.
I remind you that next week at same day and same time, so 4 p.m. chat, we are gonna discussing about more or less the same topic, but regarding 14K. Today we talk about 18K. Next week we will talk about 14K, and the relator won't be anymore. I'm sorry, Elia, but another person which is
Mm-hmm.
called Valerio. So if everything is fine, it looks that there are no questions. I remind you also that, okay, you can see here our email addresses, and you can ask us whatever you need, and we will try to answer in a deep way. Thank you very much to attend at this webinar. Thanks everybody, and I hope to see you soon next Thursday. Okay. Thank you very much,
Thanks,
Elia.
everybody.
Thank you for your time,
Thank
and
you for
bye
you
bye
to
to
attending
everybody.
the
Bye,
webinar.
bye bye,
Thank you. Bye-bye.
bye.